So we're talking today about charging choices of plug-in vehicle drivers. And so really this work is kind of motivated by the desire to answer questions like, where should we put public charging stations in order to maximize the adoption of plug-in vehicles and minimize gasoline-fueled vehicle travel? That's the question, right? In fact, that's two different questions. So my first kind of message is that we want to be clear on what question we are trying to answer, and the best design of a recharging network may depend on whether we're trying to encourage new adopters to start owning PEVs, or whether we're trying to sort of best meet the needs and maximize the satisfaction of people who already own PEVs. So those are two different questions. They may have two different answers. What I'm talking about today is really focused on current owners and drivers of PEVs and how do they use charging infrastructure. So we want to understand PEV owners' charging choices for a couple of different reasons. For one, with a good model of their choices and their behavior, we can predict demand for charging and predict the utilization of electric vehicle supply equipment. And this, as we move towards more market-driven, profit-motivated installations of charging infrastructure and EVSE, public charging stations, et cetera, it's going to be important to be able to predict where you can put a station and have it be profitable. So that's one application. Secondly, we want to understand when and where the demand for electricity is, because this affects, and I'll show you a little more on this momentarily, this will affect the source of the electricity, which has implications for emissions. It will affect the demands placed on the electric grid, and in the case of plug-in hybrid vehicles, this will affect how much petroleum versus electricity used, which has implications for their energy security benefits. And then thirdly, we want to, we ultimately think that, or what we want to do is apply these kinds of models to be able to design recharging networks that can meet consumers' needs, increase the use of battery, reduce gas-fueled VMT, gas miles traveled in plug-in hybrid vehicles. So I thought I would start as a jumping off point by showing you something that some of you may have seen before if you were on a previous webinar by my colleague Stephen Zoff, or my former colleague Stephen Zoff from MIT. I believe he showed you a figure that looked very much like this, which is, this is showing, the blue curve is what I'd encourage you to focus on. The blue curve is what we call the petroleum displacement factor, or essentially the fraction of miles that are powered by electricity rather than gasoline. And these are from an instrumented vehicle study of 125 pre-production Prius plug-in hybrids around the US. These vehicles all had the same 3 kilowatt hour battery. And what we found was that on average, about 14% of their miles were powered by electricity, but there was a substantial number for whom basically no miles were powered by electricity. And at the other extreme, there was a few who were at or around 50%, and one who was at almost 60% of his miles powered by electricity, even with this small battery. So the point is that there is a large degree of variability in the amount of electrically powered miles that you can get, even with the same vehicle and even with a very small battery. So driving behavior and charging behavior is really important for this, so we want to understand it better. And secondly, from a policy standpoint, we're kind of wasting our money if we incentivize these guys over here to adopt a plug-in hybrid vehicle. If they adopt that vehicle and either they don't charge it or their driving patterns don't really match, don't really align well with the capabilities of the technology, we're kind of wasting effort on these people here. We should be thinking about, how do we get the folks over in this region to adopt? Those are the ones who are going to get more benefit out of the technology and are going to where it's going to provide more benefit to them in terms of fuel savings and more benefit to society in terms of greenhouse gas and petroleum savings. So we have a question. Can I clarify what density means on the slide? So this is a probability density function. So all this means is that it's a relative measure of how many people fell, or how many of the vehicles in this study fell at each point along here. So it's kind of like a histogram, if you're familiar with a histogram, but it's a smooth fitted curve rather than a set of bars. That's all. I hope that clarifies. So we, okay, yes, great. So now the next thing is that we did in this work is we said, let's look, we have a mean, an average of 0.14, 14% of the miles were powered by electricity. We said, what if we kept the driving and charging patterns the same, but we changed the battery capacity? So this is where we start. We started here with a 3 kilowatt hour battery and about 14% of our miles powered by electricity. We said, what if we go to a 6, a 9, or a 12 kilowatt, 6, 9, 12 kilowatt is here battery. So we can quadruple that battery capacity, and that gets us up to around between 25 and 30% of our miles powered by electricity. So same driving, same charging patterns, bigger battery, we can get more miles powered by electricity. But we also said, what if we keep the battery the same? What if we keep that relatively small 3 kilowatt hour battery? And what if we could make it easier for people to charge? So looking over in the figure on the right here, we said, what if people charged and kept driving the way they were driving, kept the battery the same, but what if they charged every time they stopped for more than 8 hours? That would get you from 14% up to about 20% of your miles powered by electricity. And at the extreme, if you had people plugging in every time they stopped, even with this small battery, you could get up to about 28% of your miles powered by electricity. So the point here is not to say that charging is more important than battery capacity, but that there is, in both cases, significant potential to get more out of a plug-in hybrid by changing either battery capacity or charging availability. So again, there's a lot of potential here, and we want to better understand what's going to affect that decision to charge. So I mentioned before that the benefits of plug-in hybrids, or really of any PEV, any plug-in electric vehicle, depend on when and where you charge. And so what this figure is showing is the electricity generation mix. This is from Europe, not the US, as you can probably tell from the large amount of nuclear energy here. But this is the electricity generation mix over the course of a week. So from 1 to 168 hours in a week, how does the generation mix and the total demand for electricity vary over time? So the top line here that I'm tracing along with the arrow is the total electricity demand. You can see this is a Wednesday, Thursday, Friday, Saturday, Sunday, and then Monday, Tuesday. And so there's these diurnal variations in total demand. And then we also see that the composition, the generation mix, the combination of sources that provide that electricity varies. So the point is that if we add vehicle charging on top of these peaks, that could have very different implications for the grid than if we're adding it on these shoulder areas or if we're filling in the valleys. And secondly, the emissions intensity of our electricity source varies with time of day and day of week as well. So for accurately assessing the impact of vehicles, we want to be able to understand and predict when and where charging is going to occur. So how do we approach this, right? The simple view and simplistic view really would be that, we have a plug-in vehicle, we have some EVSE, the vehicle plugs in. But as we'll see, that's really not how this works out. People often pass up opportunities to charge. And what we want to understand is, you know, this is a probabilistic decision then. You have someone with an EV, they have the opportunity to charge, maybe they plug in, maybe they don't. And what we'd like to do is to figure out how various factors like the charging power or level, the price, the length of their stop, etc., affect their decision of whether or not to charge. And so we use a set of statistical tools to model these choices. Some of you may be familiar with these, others may not. They go by a lot of names, sometimes called logit models, sometimes called logistic regression or discrete choice analysis, lots of different names, but really all referring to the same set of tools. And the central idea that underlies all of these tools is that a driver is making a choice, and they're choosing to charge or not to charge, to plug in or not to plug in. And they make that decision based on the benefit, or what we call the utility of charging. And specifically, when the utility of charging is greater than the utility of not charging, they will choose to plug in. And what we want to do is to figure out how the utility of charging depends on various characteristics of the situation. So the price that they're looking at, the power of that's available to charge, how long they're stopped for, what their current state of charge is, what their future travel plans are. And what we do in this, and I'm not going to go into the details, but essentially what we do is we look at all the scenarios where someone charges or not, and we look at what choice they made, and we connect that to these or other situational variables in order to figure out basically how do people weight each of these factors in making that decision. So before I go on, is there any questions at this point? Okay, so moving on to some of our newer work, I've got two studies that I'd like to share with you today, and time permitting, I may talk a bit about some sort of ongoing and planned work. But the first study I'd like to share is a study of 125 instrumented plug-in hybrids. Much of the work on this project was done by Haixiao Yu, who's a graduate student who's recently finished up his work here at the UW. So for this study, we used the same data that we had used in my collaboration with Steven Zoff and David Keith and William Chernikoff. This is pre-production Toyota Prius plug-ins with a 3 kilowatt-hour battery. And we had almost 60,000 trips logged in these vehicles. So that was the source of our vehicle data. And we identified charging locations from 3 different sources. 1, we inferred them from our vehicle data. 2, we got data from the Alternative Fuels Data Center. And 3, we got some data from PlugShare. So, and I promised PlugShare that I would thank them and acknowledge their contributions, which were very helpful whenever presenting this work. So thank you, PlugShare. Now, as we did this, we found 3 opportunities to improve on our prior work, the work that I did with Steven Zoff and the others. So the first was that our prior work, not to disparage it, but we had what I would now consider somewhat of a crude representation of the utility of charging. We basically took all these situational variables, we dumped them into a regression model. And it's not a very smart or sophisticated way to approach modeling these decisions. So we tried to improve on that in this work. The second thing was we had previously modeled the probability of charging, but really from a design and from a policy standpoint, it's a lot more useful to know what is the probability of charging when someone has the opportunity to charge. So in our previous work, we couldn't really tell if when someone didn't charge, we couldn't tell if it's because there was no opportunity available or if there was an opportunity available and they just didn't take it. So in this work, we tried to separate those two effects out. And then thirdly, in our prior work, we had acknowledged that there might be variation between individuals in how they value these different factors, but we didn't really allow for there to be any correlation in their preferences. So for instance, some people might, when the state of charge in their battery is low, some people might put a really high premium on charging. They might have a very high utility of charging when their state of charge is low. Someone else might not care so much about that. But you can also understand that when you know someone is someone who cares a lot about state of charge, that might tell you something about how much they weight other factors like future travel distance or distance to home, other factors, day of week even. We didn't allow any of that in our previous work, so we tried to improve on that in this work. So I'd like to go through these one by one and kind of share with you what we found. So the first thing we did was we tried to come up with a more sophisticated representation of how people would value charging, or how the utility of charging would depend on the situation. So what we said was that what we hypothesized was that the utility of charging would depend on how much energy you can get during a charge. And so that's going to be limited by, it's going to be the smaller of either the energy that can be transferred from the EVSE, but it could also be limited by available capacity in the battery. So if your battery is empty, but you're only stopped for a short time, you can't get very much energy transferred. Or similarly, you could be stopped somewhere all day, but if your battery is already 80, 90% full, then you can't get very much energy either. So you need both a sufficient amount of time and sufficient capacity in the battery in order to be able to take on a useful amount of energy. So what I'd like to show you is how we kind of identify these different charging behaviors and the different situations that are limited by time versus charge energy. So we've got a question: how do gasoline price and vehicle MPG factor into the utility of a charge? So this is a good question. We don't have any variability in miles per gallon of the vehicles because these vehicles were all identical. So we're not able to figure out the role of fuel economy in these decisions. We did not look at the price of gasoline, although I suppose we could have. We did not in this work look at that. We did have data. It's over the course of a year from 2011 to 2012. I would need to go back and look at how much variability there was in gas prices over that time. There's an additional challenge as well. This is getting into the weeds a bit, but there are some limitations on the data set because we don't necessarily know, in this case, with these data from this study, we have a lot of data. One thing we don't know is who was driving the car and whether they had to pay for their own gas. Some of these were used as pool vehicles, so people might have had a gas card. So we didn't observe that, unfortunately, in this study. That's something we're driving at in the second study that I'll talk about momentarily. So in this figure, each of these points in this plot represents the end of one of those 60,000 trips. And we're characterizing that according to how long that vehicle is stopped after the trip. That's the horizontal axis here. And basically how much energy was taken on by the battery during that stop. That's the vertical axis. So, here at this point where I'm pointing, that would be a 4-hour stop where someone took on about 45% of a charge. And so there's several you can notice there's several different clusters here that are interesting. I'm going to walk you through what each of those represents and how we can identify that. So the first thing you see here is this band here along 0. So these are essentially cases where no charging occurred. Someone did not plug in. So they're stopped for some length of time, but there's no change in charge. So these are all the cases where there's just no charging. The next thing you notice is this heavy band here, this straight line up here. And what this is, these are situations where someone got a partial charge at level 1 power, but they were not stopped long enough to get a full charge. Area C here is where people got a full charge. It's basically 100% of a charge, but in this region here, they had time to spare. So basically over time, their state of charge goes up, and after about 2.5 hours, whoops, they hit their, they hit their maximum here, and then they're just sitting there and they're not taking on any more charge. This area D here is where someone got a partial charge and had time to spare. So they were able to basically, these are the folks who came in and plugged in maybe when their battery was already half full. And so then they're stopped, and even though they're stopped and they could have taken on more energy, they're limited by the fact that they were only at, they're already half full or 3/4 full or whatever. And then the area E here, these small number points out here represent the level 2 charging events. And there's a relatively small number of those, you can see, partly we think because of when this data was collected, and also the fact it's a small battery, so there's very little benefit to using level 2 charging in many cases. So I want to share now some of the results of this, and specifically looking at the charge energy variable that I talked about. So how much energy can a vehicle take on during a stop? And what this plot is showing is the utility of charging. All else equal, how does the utility of charging depend on how much energy can be taken on during that stop? So if someone already has a very full battery or is stopped for a very short period of time, they're not going to get really any benefit from that. And we normalize that utility to 0. And then we look at, well, what if they can get between 10 and 20% of a charge, or 20 to 30% of a charge? How does the utility of charging increase as that number goes up? And what we notice here is that there's a big jump here up into basically the 20 to 30% range. And once you're above about 30%, there is additional utility to being able to take on more energy, but the utility is much less sensitive to this. So this is kind of interesting because it says that if someone can get at least about 1/4 of a charge, there's a big benefit. They perceive a big benefit to that. But being able to take on, a full charge versus half a charge, that's not a very big difference compared to, no charge versus a 1/4 charge. So it's a nonlinear relationship, and we found that pretty interesting. So what we took away from this is that the charge energy variable does provide an improved description of charging behavior. Firstly, it's more grounded in sort of a theory of what we think would be a rational behavior. So that it's always nice when theory aligns with data. And we do find a better fit of the model using standard measures of fit that I've listed here. So we basically have a better fitting model. And we also found, as I said a moment ago, that there's this relationship between charge energy and utility that's quite nonlinear, with the strongest effect being below this 20 to 30% level. So people really want to be able to get at least a 20 to 30% charge. Beyond that, it has much less effect on whether they charge or not. So the next thing we did is we broke up the likelihood of charging with the likelihood of having an opportunity to charge. And what we found here, or what we did here, was we had to identify where charging opportunities were available. So as I said before, we had 3 data sources that I've listed here for this. First, we just identified all the places using our vehicle data set where we had observed charging to occur. And then we additionally considered data from the AltFuels data center and from PlugShare, which all of these folks have lists and lists of the locations of EVSE, and we went back and looked at those data based on open dates, what was available at the time of our study. And then the other thing we looked at is, well, we had to say, well, what do we mean by there's an opportunity to charge? What do we mean by you're close to a charger? And so we used we kind of explored the sensitivity to 3 different definitions. We said, well, there's charging available if you are right there. There's 0 meters distance between you and the EVSE. And then we said, well, maybe you had an opportunity to charge if you were within 100 meters of a charger or within of an EVSE, or maybe if you were within 200 meters. And you can see that the wider you cast that net, the larger the number of trips that are included. So about 32,000 out of those 60,000 trips ended within 200 meters of an EVSE. So what I want to show you here, the point of this figure is that the curves don't all align. So these are curves like I've been showing you for the utility of charging as a function of the charge energy variable. But what you see is when we filter our data set based on the availability of EVSE, it matters how we infer those locations. So when we rely on the AltFuels data center locations, we end up with a different curve and a different relationship here than when we use the other data sources. And so what this says is we better be careful about how we get our data and how we infer the locations of the EVSE. We find, though, that it doesn't matter so much. This is the sensitivity to distance. So how wide do we cast that net around each location? Turns out, at least from 0 to 200 meters, that doesn't really matter. So what matters is how we identify the locations of the EVSE, not so much are you right there, are you within 100 meters, 200 meters. So that's, we think that's an important finding for future research in this area. And so the third thing we looked at was how do we model the heterogeneity of users. And briefly, what I would say is that we used a method called latent class modeling, and essentially this is like a market segmentation approach where we assume that there is a certain number of different classes or market segments, and that within each of those, everyone is the same, but that you can have big differences in taste between those groups. And so again, back to our curve, how do these different groups value charge energy? You can see that essentially each of these curves represents the relationship between charge energy and utility for each of the 6 different classes. So we found 6 was the optimal number of classes to capture the variation in tastes. So what we see here is that the key point here is that there are marked differences between different types of users in how they value these things. So I would say that our key conclusions from this work were that the charge energy variable seems to give a better fit of the model, that we need to be careful about how we identify EVSE locations, and that this latent class approach, this market segmentation approach, seems to provide a better fit to the data. Now, do folks have questions on that study at this time? Should we pause for some questions before I say anything else?
Hear me, Don?
Yeah, go ahead.
Hi, this is Gustavo Collantes with the UC Policy Institute. I just want to ask you a question about I think it's almost the last slide you showed, which I found very interesting with the market segmentation that you did. And you found 6 different classes there. I wonder if you can elaborate on how do you define each of those 6 groups?
So what I can say about that is you'll probably find it totally unsatisfying. Essentially, what we do in this case is we model this probabilistically, so we know that each class, there's a certain probability that someone is in each class, and we basically assign those at random. And what I mean is we didn't have a lot of background data on the characteristics of the people in the different classes in this case. For the next study that I'm doing, what the student's working on right now, and unfortunately what I don't have today, unfortunately, is he's working on understanding how different characteristics like income or age or location or household vehicle ownership, how those factors can be used to predict whether people are in class 1 or 2 or 3 or so on. That's definitely something that we see as being key to be able to take these models and extrapolate them beyond just the relatively, the innovators who have been adopting these vehicles right now. Right now, people who own PEVs are not going to be, most of them are not going to be representative of the broader market. What we'd like to do is identify maybe one of these classes, maybe 1 or 2 of these classes, it will turn out looks a lot more like your mainstream consumer than some of the others. And so that's where we're going with this. We don't yet have it.
Thank you, Don. So, and let me ask you one step further. And I know this is an ongoing effort on your side, which is really, really good. And as you recognize, there is much more to be done with this data set. I think, by the way, I like to emphasize the importance of what you're doing in terms of using actual data. Oftentimes we find ourselves relying a lot on surveys because of lack of data. But seeing people's behavior in real life is really, really important to draw good lessons. But I was going to ask you, we have an audience now that is encompassing, I think, all the corners of the U.S. So somebody may be asking themselves, different regions vary in terms of driving conditions, VMT, weather, which has an impact on PEV behavior and performance, topography, and so on. So have you, and I know you can't say much about the distribution of the locations of these experiments, but can you say something at this point about the difference in behavior depending on location?
At this point, no. That is definitely work in progress. And I would say actually that most of what we learned from this particular study is more about what you need to do studies like this well, because these were pre-production vehicles. They were not bought by consumers. So that there are some limitations to these data and how well we can interpret them, and how widely we want to generalize. But what we did learn was this latent class approach seems to be really helpful. I also think it's a more intuitive approach rather than saying that we represent heterogeneity with draws from a normal distribution. I don't think has a real intuitive meaning to anyone outside of an engineer or a statistician. What we're saying here is, we've got a market segmentation. Where we do want to go is understanding, in different regions of the country, do we find that people in the South or the Southeast are really likely to be in class 6 and people in the Northwest are really likely to be in class 2, recognizing that you can have some overlap. So we're working on that now. And unfortunately, we don't yet have anything about regional differences. I also, I see there's a question from Ryan here asking about, did we record charging locations? The answer is yes, we have charging locations, and we have, it's a little hard to identify home, but in our prior work, I would definitely direct you to the prior work, and also I can share, if anyone's interested, you can contact me to follow up, and I may be able to share Haixiao's research paper, or we'll be submitting it to TRB this summer. But you know, in that case, we identified what we called home was basically where the vehicle started its day. And what we have found is when people return to the same place where they started the day, they're much more likely to charge. What we don't have is, I don't actually have the raw counts on that offhand, although that would be in the data somewhere. And then the other question I'll address is, you know, did we look at the Chevy Volt as well? And the answer is no, we didn't have those data. One of our collaborators on the original project here was from Toyota. I guess a lot of the Volt data has gone to through the EV project. As I think many folks on this call know, there were a lot of constraints placed on INL and their ability to share those data. So that's something I would love to look at in the future, but we don't have that in this data set. What we do have in this data set, or not in this data set, but in this presentation, is we have a little more variability on different types of vehicles, but relying on survey data. So as Gustavo said, you know, it's nice to have real data, or real data, I should be careful, right? It's nice to have, you know, observations, what we call revealed preference data, what people actually did in the real world. As I hope I've shown you, there actually can be some pretty severe limitations on that. It's nice to see what people did, but it's often hard to know why they did it and to tease out, did someone charge because or did someone not charge because they didn't want to or because they couldn't? And that, it turns out to be quite a challenging data issue. So one way to get around that is you administer surveys, and so that's what we did in this work. We surveyed actually BEV and PHEV owners, but the data that we've analyzed and that I'm sharing today is from the BEV owners, and this has been done by Yuan Wen, he's finishing this work up right now here at the UW, and we're working with David Keith, who's a faculty member at MIT on this.
Hey, so, let me pause for 2 seconds and see if somebody else in the audience happens to have a question that they'd like to speak up about.
Yeah, please go ahead. Sorry, I hadn't seen it.
Yeah, no. Anybody else on the audience with a question right now, or we can proceed? Okay, thank you. Go ahead, Don.
Sure. So what we did in this study was we presented plug-in vehicle owners with 8 scenarios, and we asked them whether in that situation they would charge or not. And these were characterized by the price of charging, dollars per hour, the power of charging or level, how long they were stopped, how far they were from home, how far they were from the next chance to charge, and how much range they had in their battery. In each case, it was just really simple. Here's the situation. Would you charge or not? Our respondents, we recruited them through membership in the Electric Auto Association. And you can see they were scattered around the country, but concentrated in the places you would probably expect. Our sample, we think because of our recruiting method, probably skews, or probably because of that, it definitely does skew heavily male, heavily wealthy, and very well educated. So again, some limitations in the representativeness of this sample. But what we did was, especially based on our previous finding that this charge energy variable, matters, we said, well, let's kind of take these data and put them together in a way that we think a rational decision maker would consider them. So we said, well, what are the things that should really matter? Well, one is cost, and that includes how much does it cost if I plug in here, and also how much, if I plug in here, that means, and I have a battery electric, if I plug in here, it means I don't have to plug in at home later, so that's going to save me some cost off my electricity bill. And we looked at the charge energy, how much energy someone can take on by charging, and then what we called necessity. Is it strictly necessary to take on a charge in order to get to the next EVSE. And we thought these are the things that really should be critical for determining whether someone chooses to charge. And what we found was that, the results were mostly consistent with expectations. So higher costs meant people were less likely to charge. More charge energy meant they were more likely. And if they were able to get to the next charging opportunity without charging here, then they would have lower utility of charging. But it was interesting, the effect that the charging decision would have on their subsequent home charging costs was not a significant predictor of their utility or of their charging decision. So that suggests that they're not considering how away from home charging would affect their home electricity bill. So it's a departure from pure rationality. It's not one that I consider terribly surprising, but it was certainly interesting. Now, then we said, well, let's just see how our results, if our results are robust to some different modeling approaches. So we took some of those original variables, just the simple variables like price and dwell time and EVSE power, and we just dumped those into our model specification. And when we did this, what we found was all of a sudden those variables that we thought would be so important, cost, charge energy, necessity, were no longer significant predictors of the outcomes. So people were just kind of looking at charging power and dwell time rather than charge energy. And they were looking at price. They were more concerned with dollars per hour than with the total dollars that they would spend. And they were more concerned with just what's their state of charge and how far are they from home. They were reacting to that more than to like asking, do I have enough range to make it home, right? Which is sort of how I would think about it, but apparently it's not how these people were thinking about it. So we found that really interesting, and what it suggests to us is that they may be just applying some really rough heuristics or rules of thumb based on the information they see, rather than kind of applying a careful analysis to figure out how to finish their travel day at minimum cost. So, kind of we then looked at the, figuring out heterogeneity again. We again found that latent class segmentation provided the best fit. And in this case, we found all of the classes responded to price, and a few also responded to the total dollar cost. Most respondents, I think this is an important finding, most of the respondents expressed, at least stated a preference for level 2 charging or DC fast charging. One subset, had a very strong expressed preference for fast charging. And all of them were more likely to charge when their state of charge is low, but the amount of range that they can take on, or the amount of energy that they can take on, was actually irrelevant, or is not a significant predictor. So they're really just thinking about what's my current state of charge. They're not even asking like how much, my state of charge is low, but how much can you actually get by plugging in? That didn't really figure in. It's just when the state of charge is low, they're more likely to plug in. And all of them were more likely to charge when they're further from home, but only about half considered the distance to the next charging opportunity. So the last thing I want to show you on this is basically how we can apply these models. So we took two scenarios that differed in like charging power and price and some other variables, and I don't want to bore you with those details, but just show you essentially each of the pair of bars represents scenario 1 and scenario 2. And we again found 6 classes were the optimal number to characterize this sample. And what you see is that in all cases, every class is less likely to charge in scenario 2 than in scenario 1. But the difference between those depends on which class you're in. So class 2 is much less likely. Essentially, they're not going to charge in scenario 2, period. Whereas class 3 is only a little bit less likely to charge in scenario 2. than in scenario 1. So in this way, we can see how the differences between the different types of people and the differences between situations lead to different probabilities of charging. And what we can do then is we can kind of enumerate this out over the various situations that could arise in order to predict overall charging activity. So I'm sorry, I see a question that I should address, which was, can I review what I mean by latent class segmentation? So what I mean by that is that's just the method of that's just the method that we use to characterize the differences between people. So we've got, in this case, several hundred people responding to the survey, and we are essentially segmenting them, doing basically a market segmentation. And what we found is that there are 6 different classes or segments. Class and segment are the same thing. So 6 different classes or segments. Within class 1, there's a certain set of preferences and tastes. That means that people in this class will respond one way, and people in another class will respond a different way to the same situation. So for instance, in what we called case 1 here, people in group 1, class 1, segment 1, whatever, are about 97-98% probability of charging. People in class 2 are only about 70% probability of charging. So basically everyone here is going to charge, but among this group, 2 will charge, 1 will not. So when we say the segmentation, we're just saying that we are classifying, we're splitting people up into these different groups based on their patterns of behavior. So what I see there's another question here that I can address, and I think I'd like to address, and that is, did we assess what people needed to do with that additional range? For example, the 10 miles that I get when I'm 5 miles from home is super important, but the opportunity to charge from 50 to 80% state of charge because I'm waiting for a latte and I'm already close to home is not so important. So the answer is yes and no. So I think the example given here if you need that bit of charge to make it home, that's super important. That's what we thought as well. And if you're just kind of casually plugging in because you're there and you could charge, maybe that's not so important. So we thought that would be important. That's what we thought we would see. What the data are showing in this case is that people are kind of, at least what they say they would do, is really governed a little more by just my state of charge is low or I'm far from home, not any kind of like I'm 20 miles from home and I have 15 miles of charge in my battery, and therefore I really need to charge it. It seems like people weren't saying that that's how they'd behave. And that comes to this point here. This kind of comes back to, like, study 1 said that charge energy was a better fit, provided a better fit to the data. Study 2 said these simpler variables, not thinking about charge energy or cost or the necessity of charging. Study 2 said that those things didn't really matter. And so those 2 results are somewhat contradictory with one another. And we're trying to work out why we think that is. And we think this could be because this is instrumented vehicle data. This is like what people actually did, and this is a survey. This is what people say they would do. So it's possible that people were just being lazy on the survey and not actually thinking the problem through, in which case that is definitely a mark against relying on survey data. But it's also possible that that these are that it could be due to differences in vehicle type or differences in the time at which the data were collected or something else. So we're not entirely sure. So we have a question. What are case 1 and case 2? So you asked for it. Here they are. Here's case 1 and case 2. There are differences in price per hour. You can see this is $1.50 an hour for 1 hour. This is $5 an hour for 4 hours. This is a fast charge. This is a level 2 charge. Here you can get about 25 miles of range. Here you can get almost 100. It seems suspicious to me. Well, I think it's probably limited by the range available in the battery. So you can see these are the characteristics of the two situations, case 1 and case 2, that lead to these differences. So you can see that different situational variables lead to different likelihood of charging, but that difference itself depends on what type of user you are looking at. And Ryan follows up, so people try hard to avoid the case of I'm 10 miles from home with 5 miles of range by making qualitative decisions to charge when they're far from home. I think maybe that's one thing that maybe, I mean, what was surprising here is that we put people in these, we were saying to people, you're in this situation, and some of them where you basically have to charge. And we were expecting that in those cases, it would really be almost a sure thing that people would pay anything to charge if they had to charge to get home or had to charge to get to their next charging station. That's not entirely what we saw. And one thing, though, we did get a few comments kind of in our last question was is there anything else you'd like to tell us about your charging behavior? And what some people said there was, well, you're putting me in these situations where I'd never put myself. You're asking me about situations that just wouldn't come up. And that kind of motivated some of our ongoing work. And so right now, we're at the stage of this is really ugly. This is just kind of the sketch of a somewhat complicated survey instrument that we're trying to run or trying to develop right now, where what our idea is that we want to present people with a travel day. So what people are saying is like, I wouldn't take my Leaf for a 100-mile travel day. So there's this decision that they make first, which is I have 2 vehicles in my household. I have a Nissan Leaf and I have a Toyota Camry. Here's my travel day. Look, it's 30, 40, it's 100 miles. Do I take the Leaf or do I take the Camry? And there's chances to charge along the way. But what we want to know is how do people make that first stage decision? First, do I even use my EV? And then secondly, if I use my EV, do I charge it when I get here? And if yes, then that affects the situation that I'm in when I get here. And so this is sort of a simulation-based tool where we'll actually walk people through this step by step. We say, here's your plan, or here's the planned travel day. Would you recommend taking the Leaf or taking the Camry? Okay, you took the Leaf. You're at the first stop. Here's the situation. You've got 35 miles in the battery. Would you charge, or would you recommend your friend charge? Okay, you did. Now you're at the next place. You're at 35 miles again. Do you charge or not? So that's kind of where we're going in the future. And again, we're running all of the usual risks because this is again survey data. Again, it's really hard to observe these things using instrumented vehicle data because, as I said, one of the key challenges is knowing when the EVSE is available. So I would just hop now, I think, to sort of some of our preliminary conclusions about implications. And again, the first of these is, I think we're doing some interesting work, and this is really fun and interesting work. One of the things that we really need to come up with good results are good data on EVSE locations and availability. So the ability to kind of build partnerships with local policymakers and companies who are in this business and can help connect researchers with data is really helpful to this process. Second, we did find a strong stated preference for level 2 and fast charging for away from home charging purposes. And this was the case whether when we look at it as an engineer, we say, well, you don't actually need level 2 for this. It doesn't seem to matter. People like it, whether it's strictly necessary or not. Third thing, you saw that people are more likely to charge if the price is lower. That doesn't mean, I want to just emphasize that the takeaway from that is not that we should be subsidizing or discounting electricity at public charging stations, because we need to study that further, and we need to know how does that actually affect BEV owners' decisions to use a BEV versus a PHEV, and we'd like to know, or versus a conventional vehicle, and we also want to know how does that affect PHEV owners' charging decisions. And then the final points would be, again, just reminding you that what we want to do to support current users may be different than what we want to do if our goal is to encourage future adopters. And future growth plans for EVSE, I didn't get into the analysis underpinning this. You can talk to me offline about it if you like. What you do, how you grow future EVSE, we should start thinking about whether we want to be putting this in more locations or getting more plugs per location. And the idea is, do we want to have EV everywhere, or do we want to ensure that you can get EV, you get plug-in charging anytime? So when we put more plugs at the same location, you increase the reliability of that location. So there's a question of, do we want this everywhere, or we want to make sure that where we have it, it's extremely reliable. So with that, I would thank you, and please, feel free to fire away with any questions. I know that some of you will probably have to drop off.
Thank you, Don. Gustavo again here. So this was really excellent. I'm going to open to, it's already 11 o'clock, so I want to offer some, further questions from the audience if they have any. I just want to emphasize one, perhaps simpler, but nevertheless important conclusion that I see. And you mentioned the idea that people are more likely to charge when they're further away from home. That seems to me very intuitive, but I have seen studies or reports that were kind of tending to collocate or suggesting the collocation of EVSE with the location of EV owners' homes. In other words, when they see more density of EV owners, that's where you should put the EVSE. And I feel that what you're saying here, which is somewhat obvious in some levels, it is actually no. EVSE should be put in places which are further away from the actual EV owner residence. Is that correct?
Well, I think this is complicated. This is referring specifically to away from home situations. So what this is saying is you probably don't want to put EVSE 2 or 3 or 5 miles from where people live. There's probably not a lot of points to that. But that's kind of a different question than putting it like on their block. So if you have people who don't have off-street parking, who are park in garages, shared spaces, parkades, you might in those cases, that's sort of a different use case, right? That's your daily routine charging. And what we found in this data, I think it corroborates what a lot of other folks have reported, which is that the large majority of charging takes place on a routine basis at home, overnight. I want to say it was over 80% of our people said that their typical charging pattern was, they just charge at home overnight. But we were interested, we sort of like, well, that's sort of obvious. I think that's sort of established science, and at this point that's the overwhelming majority of charging. But what we're looking at is, well, how do you make these vehicles, how do you make it possible for these vehicles to be used in more situations, and how do we predict how people will use infrastructure away from their homes? Is that clear, Gustavo? Because
that's very clear. Thank you.
You got to have that home charging, but once you have the home charging, you don't need it everywhere around the home, because you can go there and you can go home. That's clear. And I know people in Seattle are very interested in that question of what they call the garage orphans, people who would like to have an EV but don't have access to the home
charging stations. So that's an important question to clarify. Do we have any other questions, written or?
I saw there was a question from Mark Soroki about, I know it's outside the scope, he says, but do I have any thoughts about how to increase adoption using infrastructure policies? The short answer is no, but I'm trying to figure that out. So that's another area, right? So as I said right off the bat, one question is how do we build an infrastructure system that meets the actual needs of people today? And that's a different issue than how do we build a system that potential adopters look at and say, oh, hey, that's now that's easy, I want to do that. And people's perceptions before they're an EV owner, and this has been demonstrated as well, how people perceive their needs for charging infrastructure before they're an EV owner are very different than after they've been an owner for a while. And so the short answer is I don't know the answer to that yet, but that's something that I'm trying to find some support to investigate further. This question of how do we build out, what would the infrastructure look like if we want to maximize adoption for future users? That is something I'm trying to get started at. So Ryan,
any other questions from anybody?
I see a question from Ryan. Is there a stated preference for PHEVs for DC fast charge? We haven't analyzed those data yet. I suspect that there won't be. If these folks are savvy users, they will know that generally their PHEVs can't use DC fast charge. If we did find that, I would be very worried. So that is something we will look for. We'll definitely look for that in this case. Although I would have to look back at our survey. We may not have even presented people with that alternative because they can't use it in most cases. Correct, they can't use it, but do they want to? I think the way that we presented the question was really centered around like, what are the capabilities of your vehicle today? And so would you do this? We weren't saying like, in a perfect world, would you like to do this? We were saying, you're out driving your Volt, would you plug in, right? And so that's a separate question and an interesting one. Would they like to use fast charging? We certainly can't get at that from this data. Yeah, so relatedly, Rob, if your alternative to charging is using gasoline, is the behavior different than for battery electrics? So in the study, this is, I mean, I keep saying, oh, we haven't done that yet, but in the data we collected for the plug-in hybrid drivers in the survey, one of the things we varied was the price of gasoline. So I can't remember the exact range we used, but it was something like, seemed like a big range at the time, like really low, like $2, which doesn't seem so low today because we did this a year ago. But we varied gasoline price, and we wanted to see actually how do people value charging, and actually are people willing to pay more to charge their vehicle than say the gasoline savings they realize. We thought that would be really interesting as well. We expect we'll see that. We will test that. We expect we'll see something. We don't know exactly what it'll look like. And so I assume you're going back to the Rob is how much of your recorded driving could have been met with level 1 charging versus level 2. I assume that's back to this first study with the Priuses, and the short answer, never a short answer with me. I'll try and be short. The answer is that when we look at the charging events, there were very few level 2 charges that took place, and what we did find was that when I showed you, where did it go? When I showed you way back at the beginning, when I showed you this sensitivity analysis where we varied battery capacity and we varied the frequency of charging. I didn't show this. I think Stephen shared this conclusion in a previous webinar. We also looked at what if all of your level 1 charging was level 2. It turns out that didn't really make a difference. So for these small batteries, charging at a higher rate just didn't matter because the length of stop when people are plugged in is sufficiently long that you get a full charge even with level 1.
Well, I don't think we've seen other questions from the audience, right? So I think being already almost 11:10 Pacific Coast time, I'm going to thank you. I think this was an excellent presentation. Thank you very much, Don. I will ask people to feel free to follow up with you with additional questions they may have. The webinar was recorded, will be posted in our Zero Emission Map website, which is zeroemissionmap.ucdavis.edu. And I really, really hope that we can have you again in the future to share some further results on your research. Yeah.
Yeah, we'll have some more final results. I really appreciate the opportunity, Gustavo. I appreciate you all joining and sticking around. And please, if we've not had time to get to your questions, definitely please do follow up by email, dwhm@uw.edu.
Wonderful. Thanks so much, Don. Thank you, everybody, and have a good day.